Here's a quick demo for differentiation from first principles and like the thing about the limits and the h and stuff. So here you can see we're trying to estimate the gradient at point A on the curve by drawing a chord through it and then doing the rise over run. And we can just make that more accurate by just making that h smaller until we essentially get very close to 0 and it almost matches that tangent line. And that's what we do when we differentiate. And that is why that's why we say that differentiation is the gradient. And because it's the gradient, it's a measure of it's the rise over run. So it's the rate of change of rise compared to the run. And so if we make time our x-axis, that makes the derivative useful for rates of change. And that's why it can be applied there. But that's also why you get maxima and minima using the derivative, because when the derivative is 0, the gradient of the tangent will also be 0. So it'll be at a flat point in the curve, almost like a turning point. And that's why it can be used for stationary points. And obviously, if the gradient is positive, then that means the function is increasing. And if it's negative, it's decreasing. So that's why all those applications of differentiation work.